Depends.
Recover lambda.
How you recover it?
Lambda is a parameter.
So why lambda not beta?
You can identify the relationship between them, but not each term.
So in this case, I can identify something else, call it gamma, which is beta divided by lambda. Which means that I can identify the ratio between the parameters. Okay, so in this case, which is we're not going to see, but it's called identification up to a scale. It's a specific case in which we learn about the relationship of two parameters, right? So if this is 2, it means that beta is twice as large as lambda, but we don't know if beta is very small or extremely large. We don't know the levels of beta, we just know how it relates to lambda. Okay, so it's another case, another example which gives you an idea of what does it mean to reach identification. Now, if I want to identify beta and lambda here, what do I need? What do I need if I want to identify beta or lambda?
Assume one of them.
We can assume one of them, right? So you can take a theory, maybe from other studies, and say, well, if lambda is equal to, generally in other studies, lambda is equal to 0.2, then you can somehow, if you estimate gamma, then you can recover beta. Or you need another equation. Right? Here I have two unknowns, one equation. Simple as that. If I have two unknowns, I need another equation. Okay, so if I have two unknowns, two equations, I can recover both. So in other words, it means that if this is in my model, I will need some other relationship that allows me to recover at least one of the two, or the ratio of the two. So we call this identification up to scale. Now, most of the situation we're going to see is going to be about case 2, right? So next time we're going to look at linear models. You will have to be careful about point identification and no identification, also in the OLS. And the reason being that, as we will see in the OLS, this is sometimes taken as given, but there are cases that we will see that also the OLS is not identified. And generally you don't see because softwares make adjustments for you such that you're going back to point 1. Right? So we will see the case of, for example, if you put in the OLS, if you put two variables which are correlated to 1, which are collinear, you will see that softwares are going to drop one of those. Okay, so they drop one of those because that model, as we will see tomorrow, is not identified. And by dropping one, it becomes point identified. And we will see.
Question. So, what was the assumption for you in the example 2 to make it identifiable?
So we will see that tomorrow.
Oh, yeah.
So the assumptions are going to be the OLS assumption. All the OLS assumptions are starting from this model. So OLS assumes this linear model. Okay, so the linear model says that relationship, of course this is now in the example there is linear algebra, but you can write it in matrix algebra. Right? So this is many axes, this is many parameters. The OLS is assuming linear structure. Okay, so y is determined by x beta. We will see what it means tomorrow. Plus an error term. Okay? And notice that the plus error term is an assumption. Okay? It's an additive error term. That doesn't mean that a model can have this, right? So multiplicative error term. Okay? But the OLS makes the simplest assumption. It's a linear model with U. Now, as we will see tomorrow, we're going to start from this and making assumptions such that we can recover beta. But without further assumptions, we cannot do that because the OLS assumes that this is unobserved, which means that if you are in this situation here, you can try to move things around, but you're always going to have one equation, one unknown, but this is another unobserved variable. So I cannot really solve for it. We will see tomorrow that the simplest, the trick in the OLS is going to be to work with averages, okay, with expected values, and to work with multiplications. Okay? So to give you an anticipation, what the OLS is doing is to, instead of working in one equation, I observe so let's assume that this is just one variable, okay? One variable, one parameter. What the OLS is doing is to work in covariances. That's what the OLS is doing. Okay? So it's thinking about the covariance between y and x, which is going to be equal to beta covariance xx plus covariance ux. That's the core assumption of the OLS. Now you see that if you want to identify beta, now obviously you need to assume that this is 0. Right, so that's the core assumption of the OLS. And the reason why you got that assumption is not because somebody came up with a random assumption, but because I start with this model and I want to identify beta. The only way to deal with it, I need to get rid of u. And the way to get rid of u, what the OLS is doing is to work everything in expected values. In this case, would be a covariance. In that case, if I assume this becomes 0, everything else now is data, right? So this is the covariance between x and y. This is the variance of x, okay? Which means that beta is just the covariance of yx divided by the variance of x. But this is what the OLS is doing. If we just assume linearity, which is what we have assumed up to here, then we are left with this problem, and there's nothing else we can do. Okay, so we're gonna go back to this in the linear modeling. We're gonna apply these concepts in the tomorrow when dealing with the linear model. To give you an idea about identification, especially point identification in the OLS, what we are doing is exactly graphically there, right? So we start with some points. This is the case of a linear model. Notice that the linear model is exactly assuming that, right? So it's assuming that x beta is giving us a slope plus the error term. Okay, so the error term is just creating a noise around the slope. That's the assumption we are making. But notice that if we are here, we cannot assume this because we don't know what u is. And the OLS is going to assume that the average of that u is going to be 0. That's the idea of identification. Not to distinguish, this is very important, to distinguish with precision. Tomorrow we will be dealing this in steps. Okay, so we will first show identification, which means that we will be recovering beta. That's step number 1. Step number 2, which is generally represented in this way, is precision. Okay, so precision is going to tell us how precise is beta. In all statistical tables, you will see, I'm sure you've seen many times, you have first column, which tells you beta. That's derived from identification. Second column, which tells you standard error. Okay, so the standard error tells you how dispersed is my estimator, how precise is my estimator. But it's independent from identification. Okay, so identification is unrelated to precision, and we will show that more in detail tomorrow. Okay, so we solved this. So these are the 4 main questions, as I said, you have to ask before starting any empirical work in microeconometrics. Okay, so we focus on causation, population of interest, type of data available, and identification. How is my model dealing with identification? Obviously, we're going to start with linear models. Linear models will mostly focus on point 1. Type of data, as we will see tomorrow. OLS focus on cross-sectional data. Okay, so I don't have time. It's just one figure of a random sample at one point in time. And we know it's identified, right? So because the assumption implicit in the model are going to show how to achieve identification. So the only step we have to do when applying OLS is to say, I know my assumptions, okay, so there are not many, there are 3 assumptions. Are these valid? If they're valid, identification is given because it's been shown by people a long time ago. If not, I don't achieve identification. Okay? So I don't have to discuss that in detail. Okay, so let's move on to the general microeconometrics approach now. So if we are dealing with these 4 topics, then what can we do in general? What we are trying to do in microeconometrics in general. So we need to reintroduce some concepts from statistics, and I think you already know, obviously. So what is a density function? Are you all familiar with density functions? Yes. Okay. So just to remember some notation. Okay, so to the left is the density function f. Is telling us about probability of observing certain value of a random variable. The area below that function is telling us the probability to observe a random variable within certain intervals. Right? So in this case, we take a point A. So the area to the left of point A is the probability of the random variable being smaller or equal to A. More importantly, this probability, okay, so if we compute this probability from A to minus infinity to A plus infinity, is giving us the cumulative distribution function. Okay? That cumulative distribution function, if you don't remember, is telling us for a specific value A, what is the probability of observing that value. Okay, so which means that when it's going to be minus infinity, this is 0. When it's plus infinity, this is 1. Okay, so these are standard properties of random value. Now, when this is 0.5, what is A? How do we call A?
Mean. The median.
Mean or median?
I remember why.
Or both. So when the variable is distributed normally,
It's the
Then
same.
it's both, right? If it's normal.
is the mean and the median are the same thing. Okay, so that means that 0.5 of the distribution to the left, 0.5 is to the right. As we will see, this is not always the case, okay? Especially when we're going to move in nonlinear models. The median or the mean are not going to be, might not be exactly the same if the variable is not normally distributed. Okay, so when this is 0.5, A is the median, okay, to be sure. Then in some case, the median is the same as the average, if this is symmetrically distributed. Now, if we do an extra step, we can think of these distributions to have dimensions. Okay, so imagine that this is the distribution of wage, and as we've seen before, okay, so the distribution of wage depends on education, which means that for a given level of education, I'm going to have a distribution of wage. Right? So when you're going to be finishing the master, hopefully you're going to get a job, and every one of you will have a different wage. Okay? So there's going to be a distribution of wage within the same, say, level of education achieved. That means that something that we are more interested on, so I call it X in this case, is not cumulative distribution function or density function per se, but in microeconometrics, we are interested in two conditional density functions. Okay, so think of this as being three-dimensional, multi-dimensional distribution function. So graphically, it's going to look like this. For every level of X, okay, you're going to have a different cumulative or different density function. But the idea is just very simple, right? So for a given distribution of X, given value of X, some people will have high wage, some people will have low wage. Now, if you want to see that, let's assume that there are only two. In the simplest case, X is a dummy variable, say low education, high education. Then the distribution of wage, which might not be normal, might be looking like this. So what do you notice? Maybe actually to make things different. What do you notice about this? This is a very simple case, right? So this is a case in which I can divide individuals in two groups. Okay, all of my data has two groups. Let's say that my data only has education and wage, and my data can be divided just in two groups in that case because X is the dummy value. So X is continuous. Notice that the number of the distribution will become continuous too. Right? So I might have one distribution for 0, one distribution for 1, 2, 3, 4, etc. So I might have many distributions. In this case, to visualize, understand things easier, we can focus on just two groups. So what do you notice about these two groups?
Different distributions.
Exactly. There are different distributions. But generally, when you think about comparing groups, what do you generally focus on? Do we really do that?
The variance. Because we do ANOVA analysis.
Yes. So what moment do you generally focus on?
The first moment, the
First
second,
moment, the mean.
second central moment.
The average. In general, when you compare groups, I mean, if I'm asking you, compare group 1 with group 2, how many people are gonna answer, yeah, I'm interested in the third moment? Not many, right?
So
Because to get moments, you need data. You need a lot of data, right? Generally, as I said, this is just two groups, so maybe I can look at the distribution in two groups. But if I have a sample of 100 individuals and these has 20 categories, the distribution are not going to look like this. Right? So in the data, they're going to look more like something like this, right? They're not going to look like a continuous because I don't have enough data to look at distributions. The reason why generally we look at means, right? So it turns out that, as we will see more in detail, that most times, in this case, I didn't draw them symmetrically, so the mean is not going to be here, maybe it's going to be here and here. So sometimes you just look at means, but if you look at mean, you forget, or you lose a lot of information, right? So, as you were saying, if you can compare these two distributions, you have dispersion. For example, if these distributions ends here, you will not have Elon Musk here, right? You will not have very rich people there, and just the average is not sufficiently informative. Right? It's informative, but I'm losing a lot of information. So ideally, which is what we are interested in. So microeconometrics is not, or the general microeconometrics approach does not want to say about how does X goes on Y, but we want to know how the distribution of Y change when X change. Okay, so this is a conditional density. If you put these together in this figure, that's a conditional distribution.
That's overlapping.
What do you mean?
Overlapping the distributions.
Yes, this is putting these two in a three-dimensional. Obviously, in real application, we're gonna have many axes, which means that graphically cannot be repeated, right? Because we will have more than 3 dimensions. This is just a simple case. But what I'm trying to say is that the real objective is studying this conditional density. So I want to know when I change X, not how Y change. I want to know how the distribution of Y change. And the reason being that when I go from 0 to 1 in this simple case, there are many things that change. The average shift to the right, the median might change, this distribution becomes more compressed, this distribution is larger. So if you are thinking about how does education, again, if this is education and wage, how does education change wage, then ideally what you want to know is everything. Okay, so it's the whole distribution of wage, not just one value of wage. For example, I might be interested in the extremes, or I might be interested in extremely the one that gets the very low wage. As a policymaker, maybe I don't care about the rich one, I care about the poor one. So if I get education, maybe I'm pushing everyone, but I also don't stop getting people here to the very left. So maybe I exclude, I can remove poverty. Okay, so the general microeconomics approach goes in this direction. So the question is, if I change X, how much the distribution of Y change? And I do this in the following way. Okay, so we start with this. I discuss whether beta is identifiable. I take a random sample, and then I use a random sample to estimate. Now, what is the problem? What is the core problem in this assumption? Notice that this will have some parameters too. Okay, so my objective will be to estimate the parameters in this. What is my problem? What is the problem in this approach? If you think about identification, how many unknowns you see here? Or let's say, how many types of unknowns? First type of unknowns is the parameter. What is the second type? Is the function, right? So in all of these problems, we have an identification issue because the problem is just too complex. There might be, so if I only, remember that the only thing I observe is y and x. If I have y and x, I might find many, maybe infinite combination of betas and different functions that always deliver the same set of y and x, which is the same problem as we've seen earlier in alpha plus beta x plus u. So if I don't know u, then I don't know beta. I can find infinite combination of beta and u that will always solve for this equation. And the reason being that I have one equation and too many unknowns, which means that solutions are going to be infinite, unless I make certain assumptions. So this is exactly the problem that we face in microeconometrics. So we want to study how x changes the distribution of y, but we have too many unknowns. Most probably, we need to make assumptions. Now, how does microeconometrics approach this problem? And the approach is two. The first one, we focus on betas and we make an assumption of f. That's we call parametric econometrics. The second assumption is we forget about beta and we try to estimate f. That is called non-parametric econometrics. Let's make an example. The simplest parametric econometrics example is the linear model. In this case, alpha plus beta x plus u. What is the linear model telling us about this?
Linearly, we're assuming a distribution of a form of the function, which is linear, no?
The core assumption of the OLS. So how did we say we solve for you? We take expected values. We're going to see that in detail, so this is just like the intuition. The OLS make an assumption on this. Alpha plus beta x. Okay. So the OLS tells us that the average of y for a given value of x, it's a linear function. It's alpha plus beta x. Why this is important? Because the OLS, which is parametric, doesn't study the distribution, but studies what? The averages. Okay? So the OLS, it says, let's forget about distributions. We cannot recover everything. Okay? So the OLS is telling us we're going to be modeling the averages. Notice that the way it's modeled is that this is alpha, and this is alpha plus beta. Now, what is the OLS is telling us is that if I go from 0 to 1, the average goes from alpha to alpha plus beta, which means that the effect is beta. But importantly, the OLS focuses on means. It doesn't focus on extremes, which means that this distribution can have any shape. All I care is the average. This is particularly important because all of these designs is like medical research is based on this design, right? So you have one outcome, health, two groups, placebo, drug. That's exactly what medical research is doing. And it's not comparing the distribution, it's comparing the averages. So a drug is good if the average person gets better, but doesn't care if some percentage dies, because it's the average that matters. That's what OLS is doing. Okay? We don't care about extremes, we don't care about distribution, we care about averages. And the reason, as I said, the reason why we are doing that is because these problems suffers from identification. Okay? So the dimension of this problem is too big. We cannot learn about how distribution change unless we make certain assumptions. Okay? So we're going to see the other extremes, which is going to be the maximum likelihoods, which is doing something different. If I cannot recover both, then what I do, I assume what f is. I can assume maybe f is a normal distribution, and the only thing is left is beta. This is a different type of approach, again parametric, that allows to solve this. But the OLS is an easy example to see how we just focus on a specific moment, and that's what the OLS is doing. Okay, so these are examples of parametric, non-parametric specification for the average, for the conditional mean. Okay, so here. Obviously, the OLS is the first one. Okay, so the OLS it says saying that the average of y conditional on x is a linear function. Okay, it means that I can go from one average to the other just by multiplying by adding a constant and multiplying that variable x by some parameter. So that's the OLS. Semi-parametric, okay, is going to include some parametric part here inside of another function that I need to estimate. So we're going to see that application where we're going to look at probits and logits. And what we're going to see now is a non-parametric. Okay, so non-parametric does not make any assumptions about h. Okay, so we know that the average is some function of x, but we don't know what it is. Okay, so in this last 20 minutes, let's have a quick introduction to a few non-parametric methods, why they're useful. So the remaining part of the course will be about parametric methods, because these are allowing us to study better this relationship. So non-parametric methods are very easy and interesting to describe data, to try to understand relationship with data. The first method that you can get is empirical CDF. And so that's a very simple one. So we said here that cumulative distribution function is defined by this, right? So the cumulative distribution function is the probability of y being smaller than a certain value. This is telling us how this is distributed. Why I want that? Many reasons, right? So I want to know how concentrated my data is. I want to know whether it's normally distributed, so symmetric, asymmetric. So this gives me a little bit of information about how a single variable, okay, so not x and y, right? So either y or x are distributed. So if you're interested into an empirical CDF, it means that I want to build the distribution of my data empirically. It means I want to reconstruct the distribution of, let's say, wage, knowing that wage is distributed continuously, but I want to do that in my data. Okay, so how do I build a cumulative distribution function? This is straightforward, right? So if this is the cumulative distribution function, is telling me what is the probability that my data is below a certain value, then how do I do that? Which is written in that formula, but it's easy and it works. So how do I compute the probability of my data being smaller than a certain value? This is my data. So 10, 20, 5, 100, 50, 20. How do I compute the probability of my data being smaller than 15?
Take the number of the number of observations that comply with the rule you're putting and divide it by the number of total observations.
So the probability is just the share of observation that is below that value. Right? So this probability follows in two steps. I build a dummy variable that tells me whether the condition is valid. Is valid 1, 0, 1, 0, 0, 0. Here I have 6 observations. This means that this is 2 divided by 6. Now, you don't have to do that by hands, but you can compute this probability from 0 to, say, 200. Every time you're going to compute a dummy variable, it's going to give you this number here. Obviously, for this variable here, it's going to be close to 0, and here it's going to be close to 1. Okay? That's how you build cumulative distribution functions. So most softwares have this implemented already. It's a very simple application. And it gives you figures like this one, right? So focus on the blue line. What do you learn about the blue line? What do you learn about the distribution of wage in this case?
Parametric approach is a good fit.
Now, forget about the parametric. What do you learn about the distribution on the blue line?
That most people like that with an hourly wage of 20, you have pretty much all the population already.
Yes, that's one thing. What do you learn about dispersion? What do you learn about symmetry? Is it a symmetric distribution? No, right?
No.
I mean, if it was symmetric,
It would be
it would be in the center of the graph, while you have small parts, high peak, and then long tail. Okay? This is telling you that the distribution of wage is concentrated towards the left. It has a long right skew, so most probably it doesn't look like normal. And you can see here because the normal distribution is plotted just by the average and the variance of the data. Doesn't really look like my data follows the normal distribution, right? So the red is different. So if I look at this, my data is telling me that it's gonna look like this. Okay, so data is compressed in a small range as a long tail. So you see that I didn't make any assumptions here. So non-parametrically, I'm computing a distribution from observed data. Okay, so this would be an underlying cumulative distribution, density from a cumulative distribution function. Now, as you know, when you look at wage, people look at logs to get rid of long tails. Okay, so if you take the log of wage, right, so now it's going to look like this. What is this telling us? It's telling us now that if you take in logs,
it's normal.
it looks normal. Right? So wage is distributed most probably as a log normal. Okay, so if you take a log of a variable, it's going to revert to normal distribution. And you can see this because this is the cumulative distribution function of a normal. Remember that it looks like this. It's going to be useful later on in later classes. But you see that the blue line follows exactly the red line. So now the red line is given by a formula. That's why it's nicely smooth. It's a formula that takes the average and the variance of the data, the sample average and variance of the data. The blue line, you see, it's coming from data. Why do you think it's as steps? It looks more like a step function. Why is that? If you look at this data.
Oh, because it's discrete. Like the values are discrete. It's like there's no continuity.
Exactly. Okay, so because in the data, variation is limited. It's more limited, which means that I'm not going to have 10.001 and 10.002. I might have 10 and 11 or 10.5, something like that. So variation is not continuous, which means that my function represents jumps. Right? So at some point here, in this case with 6 observations, we're going to have many jumps, only jumps. So that means that for these variables to perform nicely, I need a lot of data and I need a lot of variation in my distribution. Otherwise, it's going to look like discrete. Now, how do I go from one to the other? Do you remember from basic statistics? Yes. Okay, so the derivative of this is going to give me the density, but the integral of this is going to give me the cumulative, right, by definition. So that means that if I know the CDF, I know the density. I know the density function. there are two ways of computing density. The first one is the histogram. The histogram is a non-parametric approach that gives me the density of my distribution, right? So ideally I want this, right? The easiest way to compute that in any software is to say, well, let me split this into groups. I take a midpoint and I'm going to compute the share of observations that are in between that point. Okay. This is the histogram. Okay. But the histogram is just taking a distribution, okay. I split it, and I'm computing how many observations there are in that group. So in some way, it works exactly like this. But instead of having minus infinity, I have two values, right? So left and right. So if I want to know how many observations there are in this point here, and I know how to compute this, then I need two, right?
Then you need
I need this one
and the other one.
and this one, right? So the difference of the two is telling me the percentage of observations that are in here, which is what the histogram is doing. So it turns out that the histogram is just, you don't have to know this, but the histogram is just a derivative of this in between 2 points. Now, if you want to discretize that derivative, you can compute it as we just said, right? So I take 2 points, take point, call it A, and then plus H is this one, and A minus H is this one. Okay, so I choose to split my distribution. Then the histogram is repeating this for each point. Now notice that I have many things I can choose here, which is primarily H. I can compute this in very fine groups, or I can compute this in very large groups. So this is an histogram, right? So, I mean, this is something that you know already. This is the histogram of wage. It's not surprising because we knew from before that the cumulative distribution function is telling us that it is compressed towards the left, right? This is because it is censored at 0. There's no negative values. And it has a long tail. Right? And this is exactly what we observed in the data. If you take the log of wage, again, you get normal distribution. Now, histogram is interesting, but in non-parametric is not so interesting because it doesn't look very nice, right? So what we want is to estimate density functions. Okay? A density function is different from this because the density is continuous. Okay? So like the normal distribution is gonna look like it is continuous. So we move then into what we call density function. Now, all software allows you to estimate density function, which is just a histogram making it continuous. Now, to get the intuition about density, it doesn't require a lot. So how do you go from this to a continuous function? So how do you go from this histogram to something that looks like this without using a formula? And remember, this is non-parametric. Obviously, one way is the one we have seen before. So we assume it's normal, which means I only need the average and variance. I plug it in the formula, and I get the red line. That's parametric approach. But I want a non-parametric approach. So how do I make this continuous? Any idea? If you want to have this continuous, what do you want? Many points.
Yeah.
How do you get many points? But you need large sample size for sure if you want to make it more continuous. Otherwise, it's going to look like steps again. But in this case, how do you make it continuous? we make it h small.
Yeah, that's much possible.
Instead of computing it in large H, I will compute many. So instead of having only one big group, I'm gonna have many small groups. Go to the extremes, make H close to 0. Very small. Now, what is the problem with that? As you were saying, that if I want to make H very small, I need to have a lot of variation and a lot of data. So in reality, going from here to here, I might not have any difference because I have jumps. Right? Notice that any software, when I use the commands that creates an histogram, it doesn't ask you age, right? But you can set age if you want in the options of most softwares. Age is computed automatically to give you a nice visualization of data. There's a rule, there are different rules to compute that. And the reason being that if I don't have much variation, I cannot have many bins, right? Because the data is gonna look terrible. It's not gonna look like this, but it's gonna go down to 0, then higher, 0, higher. It's gonna look nice. So if you make it small, then you enter into that problem. Okay? So if you make it too small, you might have zeros. So say that you want probability of being in between 101 and 102. 0. There's no observation between that. So the way it works is that instead of making it h, we make it sufficiently small, but then we make it continuous. So it means that to estimate the histogram in this point, I used all observations. Okay, so I use all data points, but then I need to use something to adjust for the fact that I use points far away to estimate something closer. How do I do that? You use weights, right? So if I have observation very close to point A, I have high weights. If I'm going away, I reduce weights. So a density function is just an histogram where the histogram measured in any point, which tells me the share of points that there are in that small interval, is not just an interval but use all points, where points have lower value if they are far away. So in this setting, the formula is just given by here, right? So it's the histogram with the weight. You don't need to know the formula, it's straightforward. And the weights are of this form. Most software allows you to create different type of weights. If you use theta, for example, the run density is going to print below by saying weights used are the Panechnikov. But that doesn't mean that is the only one. What I need is that the weights have this shape here. If you're close to A, you get a high weights. If you move away from A, the weights are going to 0. Okay? Which means that if I want to estimate my histogram in point A here, these points here will have high weights. These points here we have weights close to 0, but it's used to compute the share of points that are in between these intervals. So the idea of these weights is just to create smoothness. That's what we are doing. So we go from an histogram that looks like this, which is all in steps, to an histogram that is going to look continuous, okay, so smooth. So if you visualize this graphically, this is the histogram of wage. This is the density function. Okay, so the density function is going to return the blue line. Notice that it's just the histogram made it continuous. Now, here I'm replicating again the density of a normal, just to show you again that that distribution does not look normal, but it looks like we were expecting here. So move to the left with a long tail. And notice that here we encounter that problems, as I was saying, even if we use weights, we have very few observations there. You can see it from here, right? So you have many zeros and some small points. So you're gonna have something that's not gonna behave well because we are using very few observations to estimate a point here. So even if we take points very far away, the one that gets highest weight are very few. That means that my function will be more flexible to local variation. Same if we are estimating it here. So why we want to do that? Comparing distribution, it's much nicer than comparing histograms. Generally when we are, so now I deleted, but if you are in two groups, notice that now if we have sufficient data, we can compute the two distributions. Right, so x equal 1, x equal 0, x equal 1. So we can compute the two. Overlapping an histogram is not going to look very nice, but if I estimate the two densities, I can overlap them. Okay, so if I take this one down here, so I can compare the distribution of the two. And notice that I did not assume anything about the distribution of the two. I cannot compute any number of the two. Right? So I'm not saying like OLS that I'm moving this average to this average. No. So this is just useful graphically to describe data. So if I compare the two density for the two groups, then I can say already something about group 0. The density is a bit to the left, which means most probably moving to x equal 1, push the distribution to the right. I can get some idea of the dispersion. And in some cases, I can have ideas of difference across groups. One example. Imagine that two groups differs only for rich individuals or for more educated individuals. So imagine that this is x equal 1. Sorry, the distribution. X equal 1. And imagine that this is x equals 0. So if I overlap the two, I can say that, well, careful because here it looks like they're very the same. So if you are on the lower side of the distribution of y, they're pretty much the same. So differences arise if you are to the right of the distribution. So these are used to describe data that you might find in the OLS, especially when you have only a few groups, so x1 is 0. It's useful to try to describe or understand what drives our effects, because the OLS is only going to tell us what happens to the means. It doesn't say anything about the distributions or the dispersion. So it's more useful for description. Okay, so we're running out of time. We're going to see conditional means, which is going to be an introduction to OLS next time, and how this relates to OLS, which is a pure parametric approach. Any questions? All right, then I'll see you tomorrow.